My name is Enrico Ramirez Ruiz. I'm an astrophysicist, and I have been a general member and a trustee of the Aspen Center for Physics for more than a decade. My colleagues and I are here to discuss stellar interactions. So interactions that happens between stars, black holes, neutron stars, white dwarfs for the past 2 weeks, and this is our last week. We are incredibly grateful that you open this beautiful town to us. And this is a way for us to give back to this wonderful community. And, I want to welcome you to the Heinz Pagels Memorial Public Lecture Series. Heinz was a professor of physics at the Rockefeller University. He was president of the New York Academy of Science, a trustee of the Aspen Institute, and a member of the Aspen Center for Physics for more than 20 years. He served as participant, officer, and trustee, and he was also the president of the International League for Human Rights, and we're here to honor him and his contributions. It is my incredible pleasure to introduce you to tonight's speaker, Professor Charles Gammie. He's the Donald Willett Chair in Physics from the University of Illinois at Urbana-Champaign. He received his bachelor degree in mathematics from Yale University and his PhD in astrophysics from Princeton University. He was a postdoctoral fellow at the University of Virginia and at the Harvard Smithsonian Center for Astrophysics in Cambridge. Then he joined the faculties of both the physics and astronomy at Illinois. His research interests include black holes, stars, planet formations. He's one of the most versatile astrophysicists of his generation, and accretion physics. He has worked on a wide range of problems, including, for example, the formation of the moon, planet formation, star formation. He also tries to understand how particles that move very, very close to the speed of light actually propagate in the interstellar medium. He's a leader in computer simulations of astrophysical flows, particularly studies of plasma accreting around black holes, as you can see in that beautiful image. So I would say that in the annals of science, there are really a few images. I think the pale blue dot comes to mind. That's going to have as much implications for humanity as that image that you're seeing here tonight. And it's certainly captured the public imagination. This is, of course, the first image of a black hole. And Charles actually played a central role in really linking what you're seeing that to the physics of black hole accretions. He is certainly leading the efforts worldwide, and he's been instrumental in actually creating the numerical methods that have allowed us to actually make sense of this image. Charles approached the physics, I would say, creative, always new, and incredibly daring. With superb dexterity, the execution makes him a truly remarkable and important scientist who I greatly admire. He has received, without any surprise, many accolades, including the Breakthrough Prize of Fundamental Physics, the Einstein Medal, the Albert Einstein Society, the Bruno Rossi Prize of the American Astronomical Society, and early on in his career, the Presidential Early Career Award for scientists and engineers. So he's a highly decorated scientist. It's an honor to have him here. Thank you for giving us your time, and please welcome Charles to the stage.
Thank you, Enrico, for the very generous introduction. As you get older, some of these things kind of accumulate, and they've accumulated to the point that I no longer recognize the speaker. Okay, so among the other things that I do at the University of Illinois is teach Physics 101. And hopefully, how many of you have had an introductory physics course? Yeah, how many not? Okay, so you should be fine in this talk. So I'm going to talk about this picture, which I imagine that many of you have already seen. This is a picture of the black hole at the center of our galaxy. And this was published last year, last May. This is actually the second picture of a black hole. So there was another one in 2019 of a black hole in another galaxy, which was much farther away, but much bigger. And so it looked about the same size. is this one. So I'm going to spend most of this talk trying to describe what you're actually seeing here. I'm just going to start by giving away the whole story. Okay, so what you see here is a round ring, a round orange ring. And the region in the center, we think, is the black hole. And black holes are really black. They don't give off any light. And so the light that we observe from this object, it comes from gas, very, very hot gas that surrounds the black hole. So you know when you turn on your stove that you get a flame coming out of the stove and it's bright because it's hot. And that flame from your stove might be at a temperature of a few hundred degrees. This gas that surrounds the black hole is at a temperature of billions of degrees. And so it gives off radiation using very different physical means than the flame from your gas stove. Okay, so now I want to go on and sort of explain what a black hole is. And I want to talk about why this picture looks this way with a ring, why there's nothing in the middle. Okay, so and it's a theorem that says that things never work when you actually stand up in front of people. Okay, so here's the idea. We're going to start the discussion of what a black hole is. And that begins with the notion of an escape speed. So I have a little prop here. This is a Nerf basketball in University of Illinois colors. And I'm going to toss it out there. So I hope I don't hit anyone or damage anyone. Can I do this? Okay. So please just toss it around. Then eventually, nice. And eventually toss it back to me. Okay, so the ball goes up in the air. And as we all know, what goes up must come down. Right? So if you toss that up as hard as you can, it may go up, a few tens of feet and then fall back to Earth. I want that back, by the way. Okay, so that's an example. What goes up must come down. If we had a major league pitcher here and they had a baseball, they could toss it up at maybe 100 miles an hour straight up. And that might rise to a height of maybe 300 feet and then come back down again. And that's very similar to the height that you can achieve by hitting the ball with a bat. Okay. If you took a gun, it depends on what kind of gun you had. You could fire a gun vertically upward. And then, the bullet might go up for a mile and then come back down again. So it seems like everything that goes up must come down. However, we also know that it's possible for spacecraft to get away from the Earth. Okay, so eventually, somehow, if we threw it up hard enough, and the object would, thanks. It's gone into a black hole. So if we threw it up hard enough, it would go up and it would never come down. If we throw a ball up hard enough, it would go up and never come down. It turns out that there's a critical speed where that happens. So now I'm going to show you some equations. These are Physics 101 equations. Emily told me not to use any equations, so I immediately thought about how to use equations in the talk. So this is science that goes back to the 17th century and work by Newton. So here is an expression for the energy of a thrown Nerf ball. Let me see if I can. So the energy of a thrown Nerf ball has two parts. One is the kinetic energy. So if you throw it faster, it has more energy. The other part has, Enrico, thanks so much. The other part has to do with gravitational potential energy. So you store energy in the ball as it rises up. So it goes up and then it stops at the top. Now it's stored all of its energy in potential form, and then it gives that up as it comes down and it becomes kinetic energy. All right, and we can write this, an expression for this in this form. This is the mass of the ball and this is the speed of the ball. And then this thing is the gravitational potential energy. And it depends on the mass of the ball and the mass of the object that it's gravitationally attracted to. This big M right here, in the case of the Nerf ball, is the mass of the Earth. And the R at the bottom is the radius of the Earth. Okay, so this is a simple expression. This is an energy of the ball. Energy doesn't change as the ball moves. But you can see that if you were to throw it very fast, this R could become big. So you could go a long way from the center of the Earth. And if you got a very long way from the center of the Earth, then this would just be incredibly small. And we could forget about it. And then all of the energy would be in kinetic form. Or in order to reach this threshold of escape from the Earth, you have to have that first term bigger than the second. And that defines the condition for an escape speed. Okay, and this is going to tell us what the size of a black hole is in a few simple lines. So it escapes if the energy, this thing is positive. So if v squared, just solve this thing for this, bigger than this expression. Okay, you don't have to follow the algebra, but we can write down an expression for this critical speed in terms of the mass of the object that it's escaping from, and in terms of the radius of that object, which is the R that appears in the denominator there. Okay, so from this, we can calculate what the escape speed is. So all we need is this thing, which I haven't told you what it is. This is the Newton's constant. This is the mass of a body that you're escaping from, and this is the radius of the body. Okay, so we can calculate this for astronomical bodies. We can calculate it for the Earth. The Earth's escape speed is very high. It's about 25,000 miles per hour. And then we can do this for other astronomical bodies. So for Jupiter, it turns out it's about 5 times bigger than for the Earth. And for the Sun, it's actually quite a bit bigger than for the Earth, 60 times the Earth's escape speed. Okay, so if you look at this, and you can do this calculation, a calculation that Newton did, and you also know that light travels at finite speed, which people discovered around the time that Newton was doing his work, then you might ask, what would happen if this escape speed were bigger than the speed of light? So then instead of firing a bullet up, I fire a beam of light up. It's going to turn around and come back down again. Okay, so if I do that, I could ask, if I set this equal to the speed of light and solve for the radius. And if you do this, you get an expression for the radius of an object from which light cannot escape. It's this thing. So c here is the speed of light. Again, this is Newton's constant and the mass. And this is the radius of that object. Okay, so it says for a given mass of an object, there's a radius that you need to compress it to so that light does not escape. Okay, so this is the situation as it was understood in the late 1700s and around 1800. There was work by a British scientist and Laplace, famous French physicist. And they each came on this idea. And that's where things stood for a long time, because at that time people thought that Newton's theory of gravity was the correct theory of gravity. But then around 1915, Einstein created another theory of gravity. And Einstein's theory of gravity looked a lot like Newton's theory, but had some corrections to it. And it enabled people to study objects that were this small, objects where the objects moving around them were moving at close to the speed of light. Okay, and right after Einstein published his paper with his theory, he wrote down equations that were too difficult for anyone to solve. And there was a guy named Carl Schwarzschild came along who said, it's nice to avail yourself of exact solutions when they're available. I'm looking at my collaborator down here who also believes this, sort of a little humble brag. And he wrote out an exact solution, which Einstein hadn't thought possible. And that exact solution is what we now call the Schwarzschild black hole. And it turns out that that solution has a characteristic radius in it, which is exactly equal to the Schwarzschild radius. And this is something that people who work in gravitational physics have tattooed on their arms. So this is Einstein's take on an object which is so small that has such a high escape speed that light itself cannot escape. Okay, so let me try and give you a sense for how big a black hole is. And I'm going to do that for the sun. So in that M there, I'm going to stick the mass of the sun, which all astronomers know. And it's hundreds of thousands of times, 100,000 times greater than the mass of the Earth. Then, and this, the 2 parlor didn't have good font here. This is a superscript. I'm going to put in the speed of light, and I'm going to do this calculation for the sun. Okay, and I'm going to try and put this in a context which is familiar. On this map, you can see Aspen, and each of these blocks is about 1 mile in size. And we're going to just superpose on this a black hole that is the mass of the sun. Okay. So this thing is around 4 miles side to side, and it completely blots out Aspen. Now, Schwarzschild solution was a super special solution. It had a special symmetry, didn't have any rotation in it. And about 50 years after Schwarzschild found his solution, there came along a guy named Kerr who found a solution that included rotation. You include rotation, it turns out that the black hole is small. And in that case, it can be as small as this. Okay. So rotating black holes are smaller, and black holes can have rotation, which is something that we're all interested in understanding and measuring. Okay, so that's sort of the escape speed piece and what a black hole is and how big it is. Now I want to talk a little bit about Einstein's theory of gravity and try and help you understand how it differs from Newton's theory of gravity. And one of the star players in this whole story of Einstein's theory of gravity is the planet Mercury. Okay, so Mercury, as you all know, is the closest planet to the sun. So this shows the inner solar system, and these show the orbits of the planets, so the lines that they trace out as they move around the sun. And it's roughly move on these slightly distorted circles, ellipses, indefinitely. So Mars here, Earth has an almost circular orbit around the sun. Venus has an even more nearly circular orbit. And then here's Mercury. And Mercury is actually quite elliptic. It approaches the sun much more closely at one point in its orbit than the other point in its orbit. So this is known as perihelion or periapse, the closest approach to the sun. And it's quite a bit closer for Mercury than its farthest point from the sun. Okay, so Mercury is the planet that moves fastest around the sun. It doesn't really move close to the speed of light, but it moves a whole lot closer to the speed of light than all the other planets. And so effects of Einstein's theory are greatest on Mercury, Mercury's orbit, and on any of the other planets. Okay, so here's Mercury's orbit according to Newton. Okay, so in Newton's view, Mercury is moving around and it's attracted, according to Newton's law of gravity, to the sun. And it's also attracted to all the other planets. And if there were no other planets, Mercury would just sit there on an ellipse, but the other planets tug on Mercury. And that causes the perihelion of Mercury to move a little bit over time. And you can see perihelion started out there. Now it's moving around. The whole thing is going around like a hula hoop. It's moving very slowly. You can see it takes a long time for this periapse to move. This is a very small effect. Okay, so this calculation was done in the mid-19th century. This is one of the great triumphs of celestial mechanics, was the ability to do this calculation. Enormous intellectual effort invested in this. And what people discovered was that when you did this calculation and then you compared it to the observations, it looked just a little bit different. Okay, so here is what happens when you compare the orbit that was observed to the orbit predicted by Newton. And you can see there are actually two ellipses here, and one is precessing, is turning around a little bit more rapidly than the other. In fact, it's turning around about 10% more rapidly. And this discrepancy was a major mystery and caused people to look for other planets in the solar system. They said, well, there must be another planet tugging on Mercury. And so people hypothesized that there was a planet called Vulcan that was close. That's where it comes from, Vulcan, that was close to the sun and was producing this precession. So Einstein came along, wrote down his theory, and one of the first things he tried to do was calculate the precession of the perihelion of Mercury. And he nailed it. He got exactly the right answer. And this persuaded many people that he was on the right track and that his theory of gravity, which is called general relativity, is a correct theory. Okay, so one thing that you should take away from this is that we have a high confidence that general relativity is a pretty good theory. It explains the motion of Mercury. Another thing that you should take away from this is that the effects in the solar system are really small and that Newton's theory is almost exactly right. So it just provides a 10% correction to relativity. Einstein's theory provides a 10% correction. Okay, now, if you're like me, some of you are not, but if you're like me, you first heard about black holes from a Disney movie in the 19th century. Did anybody see the Disney movie, The Black Hole? It's like Maximilian Schell in it, and I think Slim Pickens is even in it. And it's the black hole is just a vortex. It sucks everything around into it. And so to sort of give you a sense of how accurate that is, I'm going to replace the sun by a black hole. So I'll collapse it down to something that is 4 miles in size. And I'll calculate what this does to Mercury's orbit. Nothing. Okay, Mercury's orbit is exactly the same. And black holes don't suddenly, attract everything around them. The solar system would look exactly the same if somehow we were able to turn the sun into a black hole. Okay, so that's, again, on the theme of relativity, a small correction to Newton's theory of gravity. It really is. It does not qualitatively change the dynamics. Now, if you were to move Mercury, if you were to collapse the sun into a black hole and you were to move Mercury inward, it was almost at the Schwarzschild radius of the black hole, then the orbits would look very different indeed. In fact, you'd have a hard time getting Mercury that close. It would tidally disrupt. Okay, now I also want to give you a sense, since I have this plot up, of how big the black hole is in the center of our galaxy. So the one that I showed you a picture of initially. So that black hole is a long way away. How big is it really? Well, it turns out that it's just a little bigger than the sun. It's about a factor of 10 bigger than the sun. So this should give you a sense, given that it's very far away, how difficult it is to see this object, for how difficult the Event Horizon Telescope experiment was. Okay, so that's my little intro to GR. Now I want to talk about one of the really interesting effects of general relativity, of Einstein's theory of gravity, and that's got to do with the bending of light around black holes. Okay, so what do we expect a black hole to look like? So it turns out that black holes' gravitational effect even affects light that's moving around in it. It deflects the trajectory of light rays from straight lines to curved lines, and sometimes even into trajectories that look something like Mercury's orbit. Okay, so just at a very basic level, without thinking about any of that, I said at the beginning that we have hot gas around the black hole, and then we have something in the middle that's dark. And so the sort of simplest picture you should have of the black hole is like a torch, like this. So there's something dark in the middle that we can't quite see. It's surrounded by hot gas. And this is, not a bad model to start out with for what a black hole might look like. So it's brighter around the edges, you see, because there's a whole curtain of flame here, whereas in front, the curtain is just sitting in front of you. And then you just see the dark outline of the head of the torch. Okay, so this is a starting point for understanding what a black hole should look like. Okay, now, in order to give you a better sense, I'm going to do an experiment. And since we don't have black holes in the laboratory, it's going to be a computational experiment. And what I'm going to do is take a ball of gas, and I'm going to lower it into a black hole. So here's the starting point for this experiment. A fireball down here, so just a spherical ball of incredibly hot gas. And in here, I have a black hole, which you can't see. So it's like the head of the torch. And now I'm going to lower this thing from about 50 Schwarzschild radii away from the black hole down toward the black hole. Okay, so it's going to go down very, very slowly. And as this drops down, the light from this fireball is going to come out to us, but it's also some of it going to go into the black hole. And then some of it is going to go close to the black hole. It's actually going to be pulled all the way around, and it's going to come out to us again. And that's going to produce this ring of light around the edge. So the light from this thing, well, let me draw a diagram over here. Here's the black hole. Here's my fireball right there. It's giving off light in every direction. Some of it comes out like this, to us. Some of it goes into the hole and is lost. And then some of it goes this, and then it goes around, and then comes back out so that we can see it again. And that's what produces this ring of light around the edge. Okay, so now what I'm going to do is move the fireball slowly around the black hole. So we're going to illuminate it from every direction. You can see now it's behind the black hole. We can still see it because the light rays are bent and they're coming over the top and bottom of the hole. Okay. And you can see actually it's right behind the black hole. There's kind of a broad band of light here, but you can also see a super narrow little band of light. And that's because we're actually seeing multiple images of the fireball. So we see the direct light, we see light that's been bent around the black hole once, and then we see light that's come around multiple times. And that sits, here's the direct light, there's the once around, then this little narrow band of brightness here is stuff that's gone twice around. So that's why the black hole appears the way it does. Now, this is not a model, the black hole in the galactic center. You don't have a fireball that's being gradually lowered on a string into the black hole. In fact, there's gas that falls toward the black hole, and as it falls, it's compressed, gets heated up like the fuel air mixture in a diesel engine. It gets heated up when it's compressed. And so we have to study what happens when all the physics that we can imagine playing a role is present. So stuff is falling in, sort of swirling around the black hole. What does it look like? So to assess what that might look like, we go to big supercomputers and we do state-of-the-art simulations. I'm going to show you a state-of-the-art simulation of this. Oh, actually, I missed something here. I just wanted to explain to those of you who aren't thinking about galaxies day in and day out, what I mean by the center of the galaxy. So this happens to be a galaxy that looks a lot like our galaxy. It's a sort of a twin of our galaxy. And what you're seeing here are lots of stars that are orbiting around a common center. Then there's a little gas mixed in with the stars, which produces some of the dark bands that you see. And the Earth is somewhere out on the edge of this, out in the suburbs. And the black hole that I showed you in the first image is right in the very, very center of the galaxy. So we sit inside what's really a disk of stars and gas, and we look through that disk down to the center of our galaxy. Right, so that's what we mean by the galactic center. All right, so now I want to do a state-of-the-art simulation. And to do that, I have the assistance of some kids at the uni primary school in Champaign, Illinois. And they are simulating a black hole. So that black cloth that they're holding up in the middle is meant to represent the black hole. And the students are going to run around the black hole like gas particles, like the gas that's accreting onto falling into the central black hole in the of our galaxy. Okay, so here it goes. Down they go. Some of them are circulating. They're mostly all circulating in the same direction around the black hole. They don't run into each other very often, which is a feature actually of the gas in the center of our galaxy as well. The atoms don't run into each other very often. And you can see that every once in a while, very, very slowly, one of them falls into the black hole. And it takes time, but eventually they'll all accrete onto the black hole. This is sort of the picture you should have of the gas. It's producing the radiation that we see. It's swirling around the black hole. It's like a whole bunch of these little flaming fireballs that are being lensed by the gravitational field of the black hole. And we want to see what they look like using the best understanding of the physics that's available. Okay, so that's what my group does. And this shows the output of one of our simulations of this process. So buried in here is gas that's swirling around the black hole. This actually looks like, gas going, I'll get to you in just a minute, okay? Water that's swirling around the drain in your bathtub. And actually there's a formal analogy to that that's quite interesting. So you see little spiral features in this thing. You see the ring around the edge, which is the same ring that was created by the fireball that I lowered into the black hole. And then you can see it's moving around. It's rotating around the black hole. Okay. All right. So this is not what we get to see, the Event Horizon Telescope, unfortunately. So it would probably take $1 trillion to put a fleet of telescopes into space, could produce an image like this. It's just not possible. So we are constrained to have our telescopes on Earth. And although someday we may put single antenna in space, and that constrains resolution that we can achieve with our telescopes. So as you may know, the resolution that you can achieve with a telescope is related to the size of the aperture. If you imagine making that aperture as big as Earth, that's what we do. And we put telescopes on opposite sides of the Earth. And the best we can do is a resolution that looks something like this. So it's a blurred version of what you saw in the last movie. So you can still see there's a little bit of stuff circulating around the black hole. This is more or less what Event Horizon Telescope sees. Okay. We can still see rotation, but it's a blurred version. It's actually slightly worse than this because we have to look through all the cruff in our galaxy to see this. That cruff also distorts the image a little bit, and we have to correct for that. All right, so this is the image that was taken by Event Horizon Telescope. This is modeled by simulations like the one I just showed you. They actually match the data remarkably well. So you can understand a lot about what this is by using these simulations. In particular, we can check that the mass of the black hole that we estimate from this. So it turns out that the angular size of this thing is proportional to the mass. So we can use that to estimate what the mass of the black hole is. And we can check that against other measurements of the mass. There's a famous set of measurements by Andrea Ghez and Reinhard Genzel and their groups that won the Nobel Prize a few years ago. And they looked at orbiting stars in the center of the galaxy and use that to infer orbits of the stars to infer what the mass of the black hole is. And we can check this against that, and it's entirely consistent. We can also try and assess whether the black hole is spinning. We can't really do that yet. It's just a little beyond the reach of our instruments. And we can also try and assess how rapidly matter is falling into the black hole. So how many bucket loads of gas are falling into the black hole each year? And that's something that we can estimate from models like this. Okay, so now I just want to say a few words about what's next for this Event Horizon Telescope project and in black hole imaging. Okay, so first of all, we think we understand most of what we see now. There's a ring of a particular size. The ring size would not have surprised Einstein. It's consistent with Einstein's theory of gravity. There's no surprises there. Gas flow around the black hole is perfectly understood. There are a few inconsistencies with the data, but we still have lots of questions. Is the black hole in the center of the galaxy spinning? This is one of the fundamental characteristics of black holes. There are two parameters that describe every black hole: a mass and a spin. We can measure the mass, but we cannot yet measure the spin. And that's what it's one of the scientific goals of what we're doing next. Okay, and we also want to know, can the black hole in the center of our galaxy launch a jet? Okay, so this requires a little bit of explanation. So there's another black hole that was imaged earlier in the center of a galaxy called M87. And if you look at an image of this galaxy, there's a bright jet coming out of the center. And the leading theory, the origin of that jet, is that there are magnetic fields close to the black hole, and those magnetic fields tap into the rotation of the hole. So the hole acts like a giant flywheel, and these magnetic fields can extract the energy from this flywheel and send it shooting away at nearly the speed, send matter shooting away at nearly the speed of light. So nothing is actually coming out of the black hole. No matter is coming out of the black hole, but energy is being extracted by the black hole and from the rotational energy, the flywheel energy of the black hole. So we think that's what's going on in M87, and we don't know if that's happening in the center of our galaxy or not. Okay. Technically, the next big thing to come out of this Event Horizon Telescope, I think, will be movies. So I showed you static images of a black hole. The next step is to revisit each of these black holes and take pictures at regular intervals in time and create a movie. And we think those movies will tell us interesting things about black holes, possibly allowing us to estimate what the spin of the black hole is. These are not going to be long movies. These are not going to be feature-length films. These are going to be TikTok videos. But still remarkable, I think, a remarkable step forward in understanding how black holes interact with their environments in the middle of galaxies. And that's it. So you will see, hopefully, within maybe 5 years, something that looks like this on the news. That's it. Thank you. I'd like to take questions, and I would like to start with you because you put your hand up first. Do you have a question? You're tired? There are probably some people out there that can relate to that. Okay. Anyone else? Yeah.
When we're talking about the black hole, you keep making it sound like it's a sphere. But when you get closer to it and the light is rotating around it and going inside of it, wouldn't it kind of seem more like a tube?
Well, so there are a lot of different ways of answering this question. One way of answering it is very mathematical. So I can just say, you know, we write down, like Schwarzschild did, solution to Einstein's equations, and they're what we call spherically symmetric. So if you take that Schwarzschild black hole and you rotate it in any direction, like a Rubik's Cube, looks exactly the same. Rubik's Cubes don't look the same, but the black hole would look the same. So that's the sense in which it's a sphere.
And if we use singularity, we going to quantum theory to a wave or a particle. Or a string.
Or a string, yeah, okay. So just to back up for a moment, if you look at these solutions that Einstein gave us, and you continue them inward through the event horizon of the black hole, through this Schwarzschild radius. Now, we have no experimental access to what's inside the horizon. But if you were to do this extrapolation, this mathematical process, you would eventually find that gravity becomes infinitely strong at the center, and that's a singularity that you referred to. And by infinitely strong, we mean that the tidal forces are really large. So the tidal forces are the gravitational force that tends to separate two nearby bodies. And that's what produces the tides on Earth. So the oceans on opposite sides of the Earth trying to separate from each other. But if you had an object that was inside the black hole and close to the singularity, it would be torn apart by this almost infinite tidal field. Now, it's a singularity, right? So that's very unappealing. That's an unappealing feature of Schwarzschild solution. And we really don't know what happens there. So this is the point, as I think there was some understanding already of in the audience. This is the point where Einstein's theory of gravity is very difficult to reconcile with quantum mechanics. And I think everybody believes that eventually we'll have a quantum theory of gravity, which will produce very small corrections to Einstein's model, which were in turn small corrections to Newton. So we'll have a quantum theory of gravity, which helps us understand what happens at that singularity. And that doesn't, I mean, this is one of the major areas of activity in theoretical physics and here at Aspen Center for Physics, but I think there's no satisfactory resolution to that yet. Okay, so I'm going to shift over there, and then I'll come down here.
Determine whether it's spinning. Is it in principle possible to observe an effect on the Doppler effect due to frame dragging of the?
Yeah. So the effect of the black hole spin is to sort of pull things around in space with the rotation of the black hole. And one symptom of this is that I could take my fireball again and I could lower it, not toward a Schwarzschild black hole, which is what I showed you, but toward a rotating black hole. And then in the example I showed you, the fireball sort of stayed still, as you know, it wasn't rotating, except at the very end when I made it rotate. It would be forced to rotate by the spin of the black hole as it got very, very close to a spinning black hole. So you can look for effects of that, frame dragging, as you correctly called it, in the models that we build. And they're there, but they're small and hard to suss out from the imperfect data that we have at the moment. And so there are 4 of us here this week thinking about exactly how to do this. We don't know yet. So you had your hand raised. Yeah.
Have you been able to, I mean, since obviously it's not a very clear picture, can you tell that stars are being swallowed up by black holes, and how do you do that?
So it's almost certain that stars are not being swallowed by the galactic black hole, galactic center black hole at the moment. And this is one of the things that Rico works on. When black holes swallow a star, if they're small enough, and the one in the center of our galaxy is small enough, they break up the star itself, and it produces an enormous outburst of energy, which is very easily observed. So the black hole at the center of our galaxy is radiating maybe 100 times or 1,000 times the power of the sun. If a star were disrupted by the black hole, it would radiate maybe a billion or 10 billion times the power of the sun. So it would be a remarkable event in the life of our galaxy. And we see that happening in other galaxies. So we do see these flares. Okay, get it in the back there.
Really admit I don't quite fully understand what you've been telling us, but the fact that we're observing a ring or torus on the picture, is that simply, again, if I'm understanding you correctly, a matter of perspective?
It really is. I think, you can think about that torch I showed you earlier. When you look directly at it, you just see black associated with the torch head, a little bit of flame in front. And that's true here as well. This isn't perfectly dark here. There's a little bit of glowing gas in front of the black hole. And then this is associated with a number of effects, one of which is sort of edge brightening that you saw for the torch. So you're looking all the way by the torch, so you're looking through a narrow curtain of gas. And then also by bending of light that I showed you in the example where I'm dropping a fireball into the black hole.
You did understand it.
Okay, yeah, in the back, and then I'll come to you.
Do we know what creates a black hole to begin with?
Yeah, that's an interesting question. I'm sorry. The question was, what creates a black hole to begin with? And there's a famous diagram of this. It's a flow chart that shows all the ways in which you can make black holes. So let me list a few. Okay, so one way you might be able to make black holes is in the early universe. You might have fluctuations in the matter density that produce black holes. And then those survive somehow to the current day. Another way that you might make a black hole is in the collapse of a massive star. So stars have a finite amount of fuel. Massive stars burn that finite store of fuel. They have more of it, but they burn it really, really quickly. And eventually they can no longer support themselves against gravity and they collapse. And they may form, if they're in the right mass range, they might make a neutron star. If they're really big, you probably make a black hole. That's another way to make a black hole. Yet a third way of making a black hole is through just direct collapse of a gas cloud. And that may happen in the centers of galaxies where there's a really dense collection of gas as the galaxies are forming. Then you can make bigger black holes from small black holes, either by merging two black holes, which is what was probably detected recently by nanograv. I don't know if there was this gravitational wave announcement. Yeah, so that's probably what they saw, really big black holes merging together. Or you can feed gas in, as I showed you for the galactic center, and that grows the black hole over time. Although our galactic center black hole is on a diet, it's eating so slowly that it's like a person eating a grain of rice every million years. It's really slow. It's growing very slowly. Yeah. So you were next. Yeah.
Yeah, what determines the direction of the spin, and do galaxies have it? What are they directional, and does that?
Yeah, that's a super interesting question. Yeah. So this is an area of active research. So not only do they have some sense of spin, but they have a direction. And you would think that if you have a big galaxy, stars orbiting around a common center, in the middle you have a black hole. The black hole ought to be spinning just in exactly the same way as the galaxy. Okay, so how do you test that? And then we can't measure spin. Okay, well, I said that black holes may be able to eject jets, and it may be true that they eject those those jets along an axis which is parallel to the spin axis of the black hole. So then jets, extend. They're as big as galaxies. They're pretty easy to observe. You look, are these jets all pointing, perpendicular to the disks of galaxies? It turns out the answer to that is no. That these jets point every which way. They're consistent statistics are consistent with them being randomly distributed on the sphere. And so somehow the stuff that's falling in must lose memory of which direction it was rotating on the way in. That may not be too surprising because it has to cover many, many orders of magnitude in radial scale to get from, you know, something the size of a galaxy to something somewhat smaller than the orbit of Mercury. Okay, yeah, and you second. Yeah.
Any new dynamics? It's early, but any new dynamics formed, any ahas with the merging of the black holes? And recently in terms of Earth time?
So from the merging of the black holes, so this is the nanograph thing, so which is not really what this, you know, this is focused on, this talk was focused. It in many respects was unsurprising.
It was not.
It was unsurprising. But it's an incredibly important achievement because it confirms that black holes actually do merge in our universe. So there was a big mystery about whether these black holes could actually get close enough to each other to merge. And that observation made it much more likely that that is actually occurring. And it changes our expectations. It makes us think that it's almost certainly what happened, that they are able to get close enough to merge. Okay, and then you. Okay, sorry.
When you were talking about the jets from the black hole, when you were looking at the M87 star black hole, the other one that had the jets, was there any difference in the spinning of the accretion disk?
Yeah. So this is a topic of current discussion. Yeah. Okay, so the first black hole that was observed is M87 star, which is notes M87 is the galaxy that it's in. Star denotes the black hole at the middle, and that one has the jet coming out of it. And the question was, I'm sorry, now I've repeated myself all the way through and forgotten what the final question was. If you can tell the difference in terms of the spin. Yeah, so we cannot actually measure the spin of that black hole yet correctly. What we do is we build a lot of models like the one I showed you, and we compare the ones that are rotating to the ones that aren't rotating, non-rotating black holes, rotating black holes. And what we find is that the ones that have rotation produce a jet, and the ones that aren't rotating don't produce a jet. So in that sense, there's evidence that it's rotating. That's pretty indirect evidence. You have to really believe the models. And even I, who create the models, don't fully believe the models. So, you know, I think what we would like to have is a more direct way of measuring what the spin is. And that's the whole game at the moment. Okay, now, yeah.
On the time scale of the since the Big Bang, when do you believe black holes began to form? Tied into that, when we look further away, we see earlier events.
Yeah.
So do you see black holes far enough away that you could comment?
Yeah. So the question is, when do black holes form in the evolution of the universe? You know, they may form very, very early in the universe. We may make even small black holes that are, you know, size of the Earth collapse down to a black hole, which would be very small indeed, like a centimeter in size. So we don't have any evidence for those yet. What we do have evidence for are supermassive black holes, like the one at the center of our galaxy and the one at the center of M87, at great distances from us, and the universe was much younger than its present age. So you know, our galactic center black hole is on a starvation diet. Okay, but some of these things are pigs. You know, they're just eating like crazy, and as a result, giving off a ton of radiation. And so we can see them from the opposite side of the universe. And one of the things that's going on in astronomy now is that people see objects that are visible even closer and closer to Big Bang. And there is some, there's a little discomfort, I would say, among people who build models of the formation and growth of those black holes, and how soon they appear on the scene after the Big Bang. So it's not yet any kind of evidence for new physics, but it's just a little uncomfortable. Okay, anyway, I'll take you.
So I actually have a couple of questions. My first one would be, given the fact that, like just building up on the idea that black holes kind of eat,
Yeah.
and what would be the problem? Like, have you ever heard about the theory of wormholes? I was just wondering, what would be the probability of these actually existing, since we don't know like what's happening in the
Yeah.
black hole?
Yeah, so there are solutions to Einstein's equations, which are what you would call wormholes. So the question was about wormholes. What do I think about wormholes? Those solutions require pretty exotic forms of matter to maintain a wormhole opening. So you have to put something in there that looks nothing like any matter that we've seen in the universe. And I'm kind of a conservative physicist, so that seems speculative to me. We don't need them. It would be exciting if wormholes existed. Again, no evidence for them yet. Yeah. I'll give you one more, and then there were a lot of questions, so I don't want to. But I'll take one more. Yeah.
Do black holes die?
Black holes die. So that's an interesting question. Actually, I have a little video of this that I'm gonna show you. Let's see if I can find this. Okay, so return again to uni primary school. So there's a notion that dates to Stephen Hawking that black holes can evaporate. And this is a quantum mechanical process, but it's not really quantum gravitational. It's quantum mechanical in the, on top of a Einstein solution to general relativity. It's a process where you make pairs of particles all the time in the vacuum around the black hole. They annihilate again, usually very quickly. Every once in a while, one will fall into the black hole and the other one becomes real. So we say these are virtual particles that appear and disappear. And every once in a while, you can turn one of those to a real particle using the process that Hawking described. And if Hawking's view were, if that was the only thing going on, the only process going on around black holes, and they would eventually evaporate. And we don't know how to describe that, but eventually we would need a quantum gravity theory to describe what happened at the very end. Now, I have a video of 3rd and 4th grade evaporating from the black hole. They leave really fast. And this process is incredibly slow. So for an object which is of astrophysically relevant mass, Hawking radiation would take many, many times the lifetime of the universe. And in fact, black holes in an astrophysical setting would grow from light falling into the black hole much more rapidly than they would evaporate through Hawking radiation. That's this Hawking evaporation process. Okay, another question. And then to
This is a person who didn't take 101. What is the fascination about? Why do we care about black holes? And what are they telling you about the universe itself? What the study of black holes tells us what?
So if you're asking, what is the fascination? I mean, one part of that about black holes, one part of that has to do with popular fascination of black holes. I don't really understand that, actually. I would say, I was in this collaboration that announced these pictures. I was completely unprepared for the reaction. I knew it was going to be big. when I went to pick up my daughter at swim practice and her teammates asked me about it. And I couldn't believe that they knew what was going on. Those pictures were seen by billions of people. So that's, it's something that I would not have predicted. For physicists, there are lots of interesting things about black holes. So they are the most extreme collapsed objects you can make in general relativity. They're sort of the fundamental particles of Einstein's theory of gravity in a way. And from an astrophysics perspective, from an astronomer, I teach in an astronomy department and a physics. The colleagues in physics are interested in some aspects of this, what it says about gravity. And my colleagues in astronomy are interested in other aspects of this. So one thing that's interesting is these jets, which again, we can see from the other side of the universe. They're very easy to observe. And if our current thinking is correct, there's a spinning black hole at the base of every one of those jets. So that tells us something interesting about the population of black holes in the universe. So there are a lot of other things, I think, but those are just two big ones. Okay.
Previously, I had learned that black holes were infinitely dense and therefore a tiny point as opposed to the size of Aspen. Has that been updated and corrected, or are there different theories about that?
Yeah, so it gets to a question of what you mean by density. So if you take the Schwarzschild radius of a black hole and take the mass of the black hole and divide by the volume inside the Schwarzschild radius, estimated in some way, we have to be a little bit careful about how we do that. Then black holes are not infinitely dense. And because the radius is proportional to the mass, they actually get less dense as you make them bigger in that sense. Now, there's nothing at the horizon of a black hole. So if you would be so unfortunate as to, ride your way down through the event horizon, you wouldn't see any signposts. You would see nothing around. You'd see some infalling gas, and it would all be going toward the singularity at the center. So something happens to that stuff when it gets to the center. This is a question that was asked earlier, and we don't really understand that. It's actually not observationally accessible to us as far as we know. There are some, it's as far as we know, it's not observationally accessible. Okay. Do you want to? So
the shuttle is leaving at 6. The shuttle is leaving at 6:45, and we want to make sure that you have enough time to get to it. But Charles is going to be here to continue taking questions on stage, so feel free to come and ask questions. And yeah, I want to thank Charles again for his wonderful talk.